So we also talk about the expectation of the function of a random variable, right? Mu of gx. No. But he told me he didn't, so. When we have sets of data in general in statistics, we know that one of the very important characteristics can be represented by mean, because mean of the data will give us a general tendency of that set of data. Now, this data, imagine it's random, so we define it as a random process. And now, when we have this random process, a random variable, we have to be able to define its mean. And we say that the mean is called expected value. Because we are expecting the mean happens. If we say that we have a class of 100 students and we do an exam and the average is, let's say, 80, so it means that if you randomly pick up a person and I tell you that what is the grade of him or her, if you say it is 80, with high probability you will be very close to the actual value that person has got. So it's an expected value. That's why we call it expected value. Also, we saw that this when we are talking about a random variable, we are having a function, right? We don't have sets of numbers. Now we have a function. So we want to see how we can calculate the expected value. You have seen the formula as an integral or as a summation. Now, let's see that what will happen if we want to find the expected value of a function of random variables. Because for the random variable, let's say x, you can define a function. And because still it is a random variable, then we can define an expected value. So the title of today's talk is talking about the expected value. Or expectation of a function of a random variable. And as usual, we'll start by saying that let's x be a random variable with probability distribution function of f of x, and let g of x be a function of the random variable x. So let's have this few terms. We know that the expected value of random variable x is noted as mu of x or e of x. The expected value of g of x is, which means that we want to calculate what is mu of jx or e of jx. So we want to calculate what is mu of jx or expected value of jx, which if it is a discrete variable, random variable, it will be gx multiplied by fx for all x values. We remember if it was a discrete value, what was mu x? Right? And if it is a continuous random variable, mu of jx is basically an integral of gx fx dx, and the integral is from minus infinity to plus infinity. note that now x is a random variable, right? As well as this, x is a random variable. What about x? What about jx? Is jx also a random variable?
The value is expected.
Thomas, is jx a random variable? I mean, yes or no question. No? What do you think?
Gx is a function of
Is it a random variable? No? Suma?
If gx is not constant, then obviously random.
Still. Is jx, I mean, we are not politicians, right? So, be very, very straight. Let's put it in this form. X is a random variable, okay? Is 2x a random variable?
Yeah.
Yes. Why? Because x is a random variable. So, what if jx is 2x? So, is jx a random variable? Yes. So, a function of a random variable is a random variable. So, note that jx can be considered as a new random variable. Because what you do, you are just doing some operation on your random variable, and the variable that we have inside our function is a random variable. It's like this. In the physics, we said t is time, and then we define ft, any function of t. Is it a function of time? Yes, it is. Although we have several, maybe a combination of t's inside there, but it is still a function of time. So let's do an example. A random current I flows through how many homeworks did I give you up to now?
One.
Oh, I am behind. Flows through a resistor with R is 50 ohm. Then probability distribution, density function for current is given as if x is between 0 and 0.5, it is 2kx. If x is between 0.5 and 1, it's 2k minus x. Otherwise, it is 0. So part A, find it's a very typical exam question. We gave you the PDF in this form, and we will ask you find the value of k, which makes fx a valid PDF. We find the expected value of the current I and find the expected value of the power dissipated, consumed, lost over the resistor.
Excuse me. I think we have done this example.
Really? It's very bad of him that you didn't tell me. So you want to come and solve it now here, if you have done it.
No, Beckman already solved it for.
He solved it for you.
Yeah.
Okay, so you know the solution. Come and solve it.
I
No, without looking at it.
Ah.
Come. Don't cheat.
Then this is the continuous case, a continuous case. Then
Yeah. What is the definition of a PDF? What do we mean by valid PDF?
the integral within the interval is so the integral within the interval is 1. It's integral, it's 1.
The integral from where?
Maybe from infinity, from negative infinity to infinity.
Maybe or sure?
No, actually, if
The integral from minus infinity to plus infinity of fx should be 1. Why?
it's PDF, that's what we find.
Why the PD? Why the PDF should be 1? I mean, the area under this PDF should be 1. Why?
Why?
Yeah.
I don't understand.
You said that the integral from minus infinity to plus infinity of fx should be 1 if it wants to be a valid PDF. And my question is why it should be 1? Why not 2?
That's the summation of area.
And what will happen? What will happen if the integral is 2?
It's coming 2, it's 1.
No, what will happen if it is 2?
There is no PDF.
Why? So what is above this number? Yes, because it shows the sum of probability, and the sum of probability is 1. It cannot be more than 1. You cannot add all the probabilities and get more than 1. Go ahead.
This is
So what is happening for other values?
it's
0, so we don't need to write it. Now, for the 2kx, it is less than 0.5. Look at the definition. Okay, it's 0.5 is not included. And the next one, 0.5 is included. So,
okay, so this is 0 less equals to
no, it's not less than equal, it's less than 0.5.
less than 0.5. Well,
Yes? Why it doesn't matter?
It's integral.
Why it doesn't matter?
When you get further, one point, the area under
The area under 1 point is 0. So less than equal or less is not changing because it's like adding 1 point and the area under a point is 0. Okay, go ahead. Yes. from 0 to 0.5 or is it from 0.5 to 1? Put a parenthesis between 2k. No, parenthesis, don't put absolute. Exactly, and delete the absolute before k is squared. Yes. And so the value of k is? Come on, you Pejman solved it. What is the value of k? 2. K is equal to 2.
Then it means f of x is equal to
4x. So, this is the fx. Now, solve part C. What is the expected value of the power?
the expected value.
And the power is P is equal to I square R. P is equal to I square R. And in the exam, we give you the formulas.
Then
Or if we don't, and you don't remember how to calculate power, you can ask, no problem with that. So, what is our random variable? Is R a random variable?
no, this is the random variable.
So what is R?
R is constant.
R is a constant. What about P?
P, it will also be random variable.
Yes, because g of x can be considered as a random variable. So what we want to do, we want to calculate the expected value of this random variable.
Then in that case, it will be
Close one more parenthesis.
like this. Like this.
E, open a parenthesis, put px,
Okay.
then close. Oh yeah, that's okay.
Then this is equals to like
Is this right? You're writing this formula.
this is for the expected value.
We want to calculate the expected value. What are you calculating?
I want to you said I should calculate it.
Expected value of P.
Oh,
So G, instead of G, you write P. Yes. No. What happened to your fx?
P of
Px multiplied by f of x dx. We are happy that Pejman solved it, right? Yes.
This will be
So let's substitute.
yeah.
What is R?
It's
50.
It's 50.
What is I?
It's these are I values.
No. What is I? What is I?
Current. Random current.
Yes, this is current, that's true, but what is I?
It's square of this.
No. Well, the thing that you show, what is it? What is it called? What is the name of this?
PDF.
So it's not I, it's probability density function. So what is I? This is PDF of I, that is true. But what is I? What I is a random variable, which is in here, in this example it is. Yes, it is current, but what is the random variable in this question? I mean, here the green writings. Let's see. Is K a random variable? No. Is R a random variable? No. X is the random variable. So what is your I?
It will be
X. I is X, so I squared is X squared. So it's X squared f of X dx. And the rest is just, you have to divide this integral into two integral and you calculate the integral, and as Pejman has solved it, that's okay. You don't need to. Thank you very much. Now, even in the statistics, when we had this mean, we said that, okay, mean tells us what is the general tendency of our value. We can look at the mean and they say that, okay, we have a class of 100 students and we did an exam and the average of the exam is 80, which means that, okay, this is a good class because we can look at the average value and decide. But another important thing when we have data and we want to process that one, we are talking about variance. And variance was telling us how much we are varying around the mean value that we have. So we talk about some solid numbers, but these solid numbers can be a random variable. So we can have an average for random variables, expected value. So we can now talk about how much we are varying around this expected value. So we can talk about variance of the random variable. Variance is very, very important in the sense that if variance is big, what does it mean? What do we understand? It means that the data has been scattered too much. And if the variance is small, it means the data that you have is very concentrated data. I'm not saying that concentrated data is good or scattered data is good. It depends on your application, on the situation. Sometimes you want to have this variance to be big. Like you have an image and you want to make the contrast as big as it is possible because our eyes is very sensitive to the change of contrast. So you want to have very high contrast. So you want to make this variance big. Or sometimes you want to be very accurate system, like you are designing some feedback for your control system. So you want to make the variance as small as it is possible. So it means that you are very, very precise and accurate. Like all the time you are getting the expected value or around the expected value. So depends on your application. You want to have different value for this variance. So you need to calculate this variance in order to be able to optimize it. Either by optimization, either you minimize it or you maximize it. So let's see how we can calculate the variance of a random variable. The variance of x is calculated as, we show it by sigma s squared of x, which is the expected value of random variable x, capital X, minus mu of x, s squared. Now, this means we want to see how much we are varying around our mean. Or we want to calculate the average of these differences s squared. So it's like that we are transforming our random variable to a new set, and this transformation is that all the values are subtracted from the mean and s squared, so we have a new set, and we want to calculate what is the expected value of this new set, which based on the definition that we have for the expected value of a function of a random variable, because this is now a function of x. So it will be, if it is in case of being continuous, it will be the integral of x minus mu squared of fx dx. Or in case of being discrete, it is x minus mu x squared of fx over x. So that's why that we talk about the expected value of gx. So the x minus mu squared, like what we had in the example of power I squared, is a new value. So remember, if value of r was equal to 1, we were getting something which is called the second moment of our random variable. So if mu of I is equal to 0, which we know that it is not, and if r is also 0, then expected value of p would be actually variance of I in this specific example. Why? Because the expected value will be defined as x minus mu squared, right? Expected value of x minus mu squared. And mu is 0. R was also already 0, so I have the x squared, which was what we were calculating. Now, you may remember also from high school the positive square root of variance is called, what do we call it? A standard deviation. Noted as sigma. So sigma is always positive. If we look at the data, if you look at the PDF, now we are talking about a random process, we can understand by comparing two PDFs, you can understand which one has higher sigma value and which one has lower sigma value, or higher sigma square and lower sigma square. So in general, the variance tell us how the data or the random process have been separated in the whole domain that we have. Assume this is fx and this is mu of x. Okay? We will talk about that this is a Gaussian, let's say, distribution. This is a PDF. Assume this is a PDF of the mu x. If I do something on my x and I make it more concentrated towards mean. In other words, if I decrease my variance, I try to make the variance closer to 0, how would this distribution look like? Who wants to draw it? Yeah. Okay, very good. How many agree with this? We want to make the sigma square smaller. In other words, we want to make the data to be more concentrated towards its expected value. How many says that this, it doesn't look as nice as my drawing, but how many of you say that this is a correct PDF? Yes, exactly. It should be a line. Because the area underneath the PDF is 1. So when you are squeezing it, we understand that we are losing all these parts. So where are they going? They will be more inside here. So, I mean, he's drawing in general in order to show that what happens to sigma is correct, but the peak will go higher and higher because the area underneath should be always 1. It's a PDF. It's a PDF, so the area underneath should be 1. Did Pejman solve an example about the variance? Don't tell me to write it and then, it's already done. No, he didn't, right? Good. Or even if he did, don't tell me anymore. And let's do an example. Well, the example will be very simple in the sense that it's similar to what we calculate for expected value of a function of a random variable. And this time the function, we know what it is. It's the random variable minus its mean squared. And for our previous example, calculate the variance of the current. So in this example, we want to calculate what is the variance of the current. What was the mu here? .5. So we know that fx is 4x 4 multiplied by 1 minus x and mu of x we calculated before that it's 0.5. So what we want to do, we want to calculate sigma square of x, which is the expected value of x minus 0.5 square, which we understand it is this integral. Right? So multiply by 4x plus 4 x minus 0.5 the square multiplied by 1 minus x. Now what you have to do is just you have to show your ability of calculating the integral, which is 4 divided by 3. We have to multiply first. It's x cubed minus x squared plus 0.25x dx plus 4 x squared minus x plus 0.25 and this minus x cubed plus x squared minus 0.25x, so it will be minus x cubed plus 2x squared minus 1.25x plus 0.25 dx. So it is 4 . plus 4 which if you calculate it, you will get the value to be 0.0417. Remember, in the exam, you will have your calculator with yourself. However, if you remember again, maybe in high school or in undergraduate, the probability and statistics, when you had the data, we had a very easier formula for calculating the variance. And an easy way of calculating variance of random variable x is sigma square of x is expected, the definition was this, right? Minus mu of x squared, which is e of x squared minus e of x squared, which is expected value of x squared minus mu of x squared. And if you use it, you will see that you will get the same results.